new infrastructure we have here in place. But now the quality of the technical quality, I mean, of our seminar should be much higher with this new camera and microphone and stuff. And the academic quality has always been top notch and is still top notch today. So we are already late. I would just let maybe Georg start immediately. For the ones who don't know him, he's Georg Brandstätter. I'm not sure how's that. Close enough. From the University of Vienna, and today he's talking about ILP formulations for finding optimal location for charging stations in an electric car sharing network. And the title already is 5 minutes of the same.
Yes, kind of. So okay. I figured if I have an hour, the title should be at least as long. Thank you all for coming. So, do I continue while this is crashing?
This will work. I think I just disconnected this cable.
Oh, let's go.
Okay.
That's not convenient.
Very interesting technology.
Let's see. Yes.
Okay, can we restart?
Here we are. Alright.
Okay, as I already said, it's a very long title, and I'll explain in a second what it means exactly. First of all of the work I'm presenting now is joint work with my colleagues from the University of Vienna, Markus Leitner, Ivana Ljubic, who is now working in Paris, and also Mario Buchmann. Please proceed.
Yes. Just sorry, 1 second.
Please don't crash it again.
Need to make sure that our microphone is on now. That the webcam is on too. Perfect.
The webcam is this.
Yep. So okay, the audio this is working, and the webcam I will fix it. Please.
Because I guess this way no one sees me. Maybe this is what is intended, I don't know.
Alright.
So while you're fixing the webcam, I can't switch to the next slide because
I do it.
because I don't know.
You have a secretary for one reason. So.
Yes.
Okay.
Okay. First, a little bit about the context of all this work and why I think it's important. This is all for the project E4 Share, which is about basically electric car sharing and how this can work and how we can help make it work with solving different kinds of optimization problems that arise in this context. This is a joint project between the University of Vienna, then AIT, an Austrian Institute of Technology, then the University in Brussels, University of Bologna, and IC Consulente company. Well, why do we even care about all of this? Why do we care about electric vehicles and electric car sharing? Well, in principle, they are a very interesting technology because they would allow us to produce less pollution in the cities, because not only do they not themselves produce any pollution, but if their batteries are recharged from, say, solar power, they don't produce any pollution at all. Plus, they're also very efficient in urban settings where usually conventionally powered vehicles are not as efficient because they have to start and stop a lot, whereas electric vehicles, they can recharge the battery by braking, for instance. So this makes them prime candidates, especially for electric car sharing, where usually you only drive within a city. So the limited range is not that much of a problem. So we can assume that, say, an electric vehicle might have a range of 100 kilometers. Few people will drive more than that within a city. But the problem is still that their range is shorter than for conventionally powered vehicles, and especially their recharging takes much longer. If you go to the fuel station to fuel up your vehicle, it might take, I don't know, 3 minutes. But for electric vehicles, it usually takes hours. So that means that they have to be recharged throughout the day or maybe throughout the week, throughout their usage. And for this, you of course need charging stations, because the idea for this is you bring an electric vehicle to a charging station, and it remains there for a couple of hours until it's recharged, and then it can be used again. And the question is, of course, where do we build these recharging stations? Because they're not only expensive, they take up a lot of space, and it's a huge investment that needs to be well done. So if you make mistakes at this level, maybe your company will fail from the very start. And so this is what I and my colleagues have been doing, trying to find out where to build such electric car sharing charging stations. Now some small assumptions. We assume that customers always pick up cars from these stations and return them to a station. It doesn't need to be the same station, but it needs to be a station. So it's not like, say, car to go, where you can just leave the car anywhere. We assume that they're always returned to a station. Can you get to the next slide? And the next slide. So now we go to the more formal problem description. We assume we're given a street network such as this grid, as you might find it in some American cities or something. Next slide. You're going to have to do this one. Okay, that's no problem. And we assume that some of these nodes are potential charging stations. So this is where we might construct or open such a charging station. Each of them has a cost for building it. We call that Fi. It has a maximum capacity of charging slots, Ci. And each of these slots, if we decide to build them, costs a certain amount, say Qi. Next. And what's very important also is we assume that each such station covers a certain part of this street network, which we call the neighborhood. And we assume that within this neighborhood, people are willing to walk to a station. So if, say, a person lives here and wants to get an electric car, we assume that he would walk there, but not here. Next one. And our objective is now to select a subset of these stations which we want to build, subject to some budget constraints. And of course, as I already said, we don't only care about which ones to build, but also how large they should be. So whether it should be 2 or 40 charging slots. Go on. Okay. We use trips now to represent the estimated demand in our network. So we assume that we are given a set of trips. Of course, these might not be exact trips, but you could imagine just an expected set of trips which we assume that our customers are going to make, and I'll talk about some extensions to this later on. Each of these trips has an origin, somewhere in network, a destination, somewhere in network, and note that this need not be a station, but this can be anywhere in the graph. They have a start and end time, so they start at Sk and return at Ek. They have an associated profit, so how much we will charge the customer if he wants to use the vehicle for that. And, which is also important for us, we have an overestimated battery consumption. So we assume that if a vehicle travels from here to there, it uses about Bk battery. And what we also do now is we select a subset of these trips which we want to accept, and we want to maximize the profit from doing so. So this one. If we accept the trip, we assign it three things. First, a start station. So this is any station where the origin lies in the neighborhood. So, for instance, for this trip, we have the origin here, and both these stations cover the origin with their neighborhood, so we assume that both might be potential charging stations. Next. Then we have an end station. In this case, there's only one. And we also, of course, need to have a car ready so that the customer can take the car from the station and drive it to the destination. Okay. Yes. Okay, so much about the problem itself, and now let's talk about the math and the interesting part.
Just repositioning.
Oh yeah.
Okay.
Okay. First, some more assumptions and definitions, and I promise this is the last slide with these, and after that, it's the models themselves. We assume that we have a homogeneous fleet of cars, so all the cars are the same. They cost the same amount of money to buy. In this case, we call it zeta. When they are parked at a station, they're always recharged at a uniform and linear rate. This we call rho. We have a certain planning horizon from 0 to Tmax. We now define this set n of a vertex in our graph that tells us which stations are in walking distance. This will be important for the models later on. And finally, we have just delta k, which is the duration of the trip. And here are now the important decision variables, and I've already told you a bit about this. This tells us whether we build a station or not. This z tells us whether how big a station should be, so how many charging slots there should be. AH tells us whether we buy a certain car. XK, and these three, you could say, are the strategic decisions we take. So this is what we actually care about. And XK tells us whether we select the trip or not. And the final one is for the assignment of selected trips to cars. So these are not exactly strategic decisions, so they're a bit outside of the domain of what we want to optimize, but this is our measurement of how well our strategic decisions perform. So we really care about these, but use these to measure the quality of our solution, you could say. Okay, next. And now this is the model itself. And you're going to have to click a lot because I'll explain each and every single one of them. Okay. First, we have our objective function, which is just maximize the profit of all the accepted trips. Next, we have the budget constraint. We're given a certain budget limit W. And up to this limit, we can build stations, we can build charging slots, and we can buy cars. Now, the next constraint is actually two constraints. It relates the capacity of a charging station to whether or not it's built. So if it is built, this is 1. So we just assure that the maximum capacity is never exceeded in this case. And conversely, if it is built, it must have at least one charging slot. And of course, if we do not build a station, then this is all 0. So a station that is not built has 0 charging slots. Now, next, we assign every trip that we accept to some vehicle. And the final constraint on this slide is this, you can imagine, is the set of trips that are active at a certain point in time. So if a trip starts at, say, time 10 and goes till 20, it's active at times 10, 11, 12, until 19. And this is just all the trips that are active at a certain time slot. And this just means that for every time slot, any vehicle can, at any time, only perform just one of these trips. So this means that there can be no overlapping trips assigned to one vehicle. And this just reduces the amount of, you could say, invalid trip assignments to cars that we can get. But of course, there is still some parts missing. The first is, so far we do not guarantee that a car moves along a consistent path. So right now a car might travel from station 1 to 5 and then do a trip from 7 to 9. And these stations might be on opposite sides of the city. And so far we don't have any way of guaranteeing that this doesn't happen. Similarly, we're not guaranteed that station capacities are never exceeded. We know that they're assigned, but we do not yet guarantee that a station with, say, 5 charging slots doesn't have 10 vehicles that want to park there. And finally, what we also don't care about so far is a car's battery level. Right now, a car can consume as much battery as it wants, never recharge, and we have no way of preventing that. So, of course, we need to extend our model to cover these things. And I'm going to present to you two models that model the first two aspects, which I'll call location feasibility, just so we have a short word that we can use to talk about all this. And then three models for the battery feasibility. Now, on to location feasibility. The first model is based on a multi-commodity flow in a time-expanded network, which we call the location graph. So this is the graph I'll be talking about a lot during this presentation. The columns represent each station, so station 1, 2, 3, 4, and the rows represent the different points in time. So this represents station 1 at time 1, for instance. And we have an artificial root and an artificial sink. Next. Now we have, of course, arcs in this graph. First we have root arcs from the root to every station at time 0, and the same for deallocation. We have arcs from the last time slot to the sink. Then we have waiting arcs, which represent that a car is parked at a certain, which represent that the car is parked at a certain station from one time to the next. And finally, we have strip arcs, and these represent that a car travels from one station to another in fulfillment of a trip. Okay, and on this graph, we now have defined a flow model to ensure the aforementioned constraints which were still missing. First, this picture. Thank you. We have a constraint that guarantees that the capacity is never exceeded. If you look at this, the vehicle flow of all the vehicles that are at a certain station and that travel along the waiting arcs of this station must never exceed the assigned capacity. If you look at this sum, this is actually just one single arc. Depending on whether if it's the last arc, this is the deallocation arc, and if it's any other vertex, it's just the waiting arc from this time period to the next. So this just assures that the flow over the waiting arcs of a vertex during any time can never exceed the assigned capacity. Next. This is cut off, okay? This is just delta minus of IT. So this is... okay, this is great. Anyway.
But that always happens.
Yeah, but online you can see it properly. So
okay.
Perfect.
It's just for us that it's
this is it's only for you.
Yeah.
Only for us, I'm sorry. Anyway, this is for guaranteeing that if a station is not open, so if this is 0, then we can no car may enter this vertex, which is kind of obvious because if the station isn't there, then the car can't park there. Next, we have that each car that is bought must leave the root vertex RS. So that just means that at the start of the day, it has to start at some station. The next is just regular flow conservation. So whenever a car enters a vertex, it must also leave this vertex by some way, either through parking or through a trip. And finally, if a car performs a trip, then at least one of the arcs corresponding to this trip, if you remember, there are these trip arcs in the graph, at least one of them must be selected by that graph's flow. So that means that if a car wants to perform a trip, it must move on one of these travel or trip arcs. Okay. This was the first model, regular flow model. And now I'm going to present to you a second model, which, for lack of a better word, I've just called no-flow model for now. I know it's not very creative, but I hope it's at least descriptive. For this, we're going to need some more additional variables. First, we have x tilde ik, which means that trip k is assigned the starting station I, and the same with x hat for the end station. And we, of course, for every trip that we want to perform, we need to select one start and one end station, always from the appropriate neighborhood. So these are the possible start stations of trip K, and the same here for the end stations. And of course, we may only use those stations which are opened as start and end stations. Then we have another variable, another additional variable, which is AIH, which tells us which station a car starts at the beginning of the day. So it's just an indicator that tells us that car H starts at station 9. Of course, again, we have to assign each car one starting station. And of course, again, we may only use those stations that are actually open. And now this is the first constraint that's a bit more difficult, so let me try to explain it in separate parts. This part in the middle represents the number of cars that are parked at a station at each point in time. So this consists of whether a car, this is basically the sum of all cars that started at the station at the start of the day. This is the sum over all the trips that left this station so far. And these are the trips that have entered the station up until this point in time. So you could imagine you start with this at the start day, and then for each time period you subtract all those cars for which a trip leaves, and you add all those cars that enter because they perform a trip. So this we can use to ensure that the capacity is never exceeded, because again, this is the number of vehicles parked at a certain time, and we just constrain it to be always less equal than the assigned capacity. And similarly, we can use that to ensure that a trip can only start at a certain station if there's actually a vehicle there. So if we know that there is no vehicle at a certain station, we are sure that this cannot be a starting station for any trip. Okay? And this is now probably the most complicated constraint of it all, and I'll take a lot of time to explain it. If you have any questions, feel free to ask me at any time. And of course, you can see it properly again.
Yeah,
this is of course a sum.
Just a sum.
Yeah, it's nothing special. Please.
Okay.
And this sum basically just tells us whether a car I starts in the neighborhood. Okay, I should probably explain this first. What do we actually want to do with this constraint? We want to ensure that if a trip is to be performed by a car, that car must at least potentially be in the neighborhood of the origin of the trip. So it must be at least potentially near a possible starting station. If we already know that the vehicle started at the other point, at the other side of town, and never moved to where we want to start the trip, we can't assign the trip to this vehicle. Okay, so now back to the formulation side. This tells us whether the car starts in the neighborhood, and of course, just one of these can be true. This is, it looks a little complicated, this is the number of times a car can potentially enter the neighborhood. So these are all the trips that can start outside the neighborhood and can end inside of it. So if there's at least one trip arc that goes from outside the neighborhood to within the neighborhood, if you think about it in the location graph, then this trip is considered to be in this set. And so this in total just means the number of times a car has potentially entered the relevant neighborhood. And next. This is, on the other hand, the times it is guaranteed to leave the neighborhood. So similar to this one, every trip for which every trip arc starts within a neighborhood and every trip arc ends outside the neighborhood, we add up here. So basically, if you flip once more, you can look at this whole expression and just look at the following. If it's larger or equal than 1, that means that the car might be in the neighborhood of the origin, so we can potentially, at least, assign the trip to it, because it might be there. Whereas if it's less equal 0, we are guaranteed that the car is not in the neighborhood, so there's no reason for us to assign it to the car because it couldn't ever perform. As well. It's important to note that this by itself does not completely guarantee connectivity, but it already prevents many invalid assignments. As I said, if a car is on the other half of town, then there's no reason to assign this trip to it. So this narrows down our search space. And if we assume that the neighborhoods for both origin and destination of all the trips are singletons, so if there's only one possible start and end station, then these constraints are enough to guarantee connectivity. So in case this is the data we have, we can just work with them and not care about what I'm going to talk about next. In general, the problem is that even though these constraints guarantee a lot of connectivity, they can't ensure it completely. Because it might just be that the car is in the neighborhood, entered the neighborhood, but is not at the correct station for which, from which we want to start the trip. And we can only prevent the assignment of such infeasible combination of trips if we dynamically add constraints forbidding them. So if we have a car that is assigned 2 consecutive trips, and the first of these ends at a different station than where the second one is supposed to start, then we have a problem, because the car is at station A and needs to start from station B and has no way of traveling there. So if that happens, we need to add one of these constraints, and these just ensure that either the car doesn't do trip 1, or it doesn't do trip 2, or it selects a different end station for K1, or a different start station for K2, or finally, that it performs at least one more trip in between these. So assume that, as I said, you start trip 1, you end trip 1 at station A and want to start the next trip at station B. One way of guaranteeing that this is possible is to perform another trip that just connects these two. Just go back a second.
Oh, sorry.
Yeah, I just wanted to briefly mention the separation procedure for this, but I guess it's pretty obvious. In the integer case especially, you just have for each trip, because we do not allow overlapping trips, we have for each trip just a sequence of trips, and we just go through them one by one and always look at whether the current and the next trip are consistent, so whether the first one ends where the second one starts. And if not, we have this situation and we just add the appropriate constraint. Now, so far we have guaranteed that station capacities are met, and also that the cars move in a consistent manner, but what's still missing is the battery feasibility, which is what's actually interesting about electric cars, because otherwise it's just regular car sharing, of course. And then we have, for this we have 3 different models. The first one is, again, based on a time-expanded network. And in this case, this models the state of a battery throughout the time period. So now this graph is rotated, so now the column represents the points in time, and the rows represent the different charging states. In this case, 20, 40, and up to 100%. Again, we have arcs in this graph, of course. First, charging arcs that represent going from one being parked at a station and therefore being allowed to increase the battery level up to the next higher level, you could say. Then, of course, if you're already fully charged, then there's no need for charging, so you just stay at 100%. And finally, if you perform trips, you deplete your battery accordingly. Yes. And again, this is just a very simple flow model in this graph. So we start at, you can't read this of course again, we start at time 0 at the highest possible battery level, Vmax, for every car that is bought. So if you go back to the previous graph, it's just this vertex. Every car that's bought starts at this vertex with the battery level. Okay. Next, we have flow conservation again. So that again ensures that if we enter, you could say, a certain battery level, we also have to leave it at some point. And finally, again, if we perform a trip with a certain car, that car has to move over one of the corresponding travel arcs for the battery. Okay. The second model now does not use a graph, but instead it uses continuous variables to model the battery level of each car at each point in time. And again, we start at time 0 and 100% or Vmax. Now, this is basically a big M constraint that takes care of depleting the battery if we perform a trip. So you can read it like this. The battery state of a car at the end of a trip is never more than what it was. We can move this to the right-hand side. Is never more than what it was at the start of the trip, minus what it took, the battery consumption of the trip, basically. And this part is just a big M constraint that deactivates this constraint for all the cases where a car does not perform a trip. So it could, in principle, also say 100 here, just fully charged. But this is an upper bound of how much a car's battery could have been recharged. Say, if a trip only takes 5 time units, then we can have only recharged for these 5 time units, so 5 times rho, which is the recharge rate. And finally, if we're not doing a trip, then from one period in time to the next, we can recharge at most rho, the recharge rate. Okay. And now, finally, we have a third approach for dealing with the battery, which is simply to explicitly forbid every path that is battery infeasible. As I just said, if we find such a path that is battery infeasible, we add a constraint of this type, where we sum over all the corresponding trip assignment variables, and ensure that in case we find a path of length 4, this fk would be 3. So fk represents the maximum number of this subset of trips that can be performed by any single car. In principle, you can also extend this and lift these constraints, but this is a potential extension for the future and not something we have done so far. Again, the constraint separation for this is, I think, rather clear. If you assume that you already have the other constraints separated, then you know that for each car you have a connected path throughout the network, and you just go through this path for each car and keep track of what the battery is. And if you ever get to a point where the battery is below 0, you know that the path so far has been battery infeasible. And of course, then again, you can try to look at the path and see, maybe you can even find a battery infeasible subpath, which makes the constraint stronger. But in principle, it also works if you just at the path you found, and eventually you're guaranteed to have only battery feasible paths. Okay, next one. Okay, now we did some preliminary computational experiments with these models. Next slide. On some rather small instances still. We assume it's a grid street network. We have up to 50 stations, where basically everything is chosen randomly. So they're randomly placed within the network. Their cost and their capacity is random within a certain frame. We have a number of trips, up to 100. Again, they're placed randomly, both with regard to their start and end location, their start and end trips times. We assume that they all have uniform profit, so we don't really care about which trips we perform, but just how many of them we do, which we think is a useful way of modeling customer satisfaction, because what customers most care about is whether or not they can actually use the car sharing system for going where they want to go. So if we assume that we say cover 95% of the trips, that's good, because it means we fulfill 95% of our customers' requests. And back one slide. Just quickly, there's 4 different variants which we evaluated. The first one is the location graph flow model with the battery graph. Then we have the location graph with continuous battery tracking. Then we have the no flow model with battery cuts. And finally, the no flow model with continuous battery tracking. And everything like CPLEX, 3-hour time limit, 3 gigabytes memory limit. And now you can go to here. Thank you. And as you can see, it doesn't look all that great. Yeah, just for orientation. On the left, you have the instance size, basically, with the number of stations and the number of trips. And then you have columns for each of the variants. And you can see the algorithm performs kind of well up to about 25 trips. And after that, it just becomes horrible. The best model usually is the location graph model with continuous tracking, which is, as you can see here, able to solve more than the others often, and especially in a much shorter time than the others. And you can also see the average gaps, and I think it paints a pretty clear picture. First, the number of trips is clearly what's defining the complexity of all this, because whether it's 10 or 50 stations doesn't seem to matter all that much, but whether it's 25 or 50 trips, very much less so. Go to the next page, please. Another question is, of course, why do these results look the way they do? And we believe one of the reasons why, for instance, the no-flow model performs so badly is because it's still missing the constraint separation in the fractional case. And as you can see here, the right columns represent the number of branch and bound nodes. And I guess this pretty clearly illustrates that there's just way too much branching going on. So we barely ever get to a point where we have an integer solution for which we can actually insert the relevant constraints. So all this gets nowhere, basically. So this is clearly something that needs to be done in the future. But first, some improvements, some others which we thought about. The first, of course, is a heuristic starting solution for the procedure to help speed up the process. And this can, in principle, be relatively simply done. I'll explain to you how this is done. First, what we care about. We want to cover as many trips as possible, but also remain within our budget limit. And one way we can do this is find paths through this location graph, which you remember from before, battery feasible paths throughout this network. So the problem of finding these paths is basically a resource constraint longest path problem. And yeah, the length is just represents the profit we expect to gain from an arc, so it's the trip profit for trip arcs and zero otherwise. And we also have this battery consumption, our resource for the algorithm. This is, of course, negative for trip arcs because there we deplete the battery. It's rho for the waiting arcs because they recharge, and otherwise it's zero. And also important to notice, since the graph is acyclic, this is the same as solving the resource constraint shortest path problem, which some of you might be familiar with, where just the arc lengths are negated. Okay. Now, just briefly about this algorithm. It can be solved by a dynamic programming labeling algorithm. A label just consists of a profit and a battery state, and it kind of represents a partial path up to a point. So I'll explain this later. One important thing to note is the notion of dominance. We say a label, L, dominates another L prime if it's better in at least one aspect, so either battery or profit, and no worse in the other. So if it has at least as much profit but more battery, it's assumed to be a better label because whatever we do to the other label, we can never be as good as the first one. So this is important for keeping the performance of our algorithm good. And now, here is some pseudocode for this algorithm, which you can't, of course, see. The idea is basically the following. You initialize the set of labels at each node. You initialize it to the empty set, except for the vertices in time 0, where you start with profit 0 and battery 100. So this represents that we have not done any trips so far, profit 0, and we have full battery. And then for each node, you basically go down layer by layer, and for each vertex, you extend all the labels at this vertex to along all arcs. So along the waiting arc, you create a label with the same profit, but rho higher battery level. Whereas for trip arcs, you create a new label with the profit of that trip added, and the battery for the battery consumption for that trip deducted from the current state. And of course, we can only do this if we always remain above 0. So if we try to extend the label and that results in a label with battery minus 10, we know that this is not feasible because it doesn't represent a battery feasible path. And we do this layer by layer until we get to the final layer and the sink. And all the labels that reach the sink with positive battery level, those are feasible paths, and we can just select the best of these labels as the next group we want to add. Okay, next. And this is now the complete heuristic algorithm. Basically, as long as we have still some budget remaining for another car to be added, so to speak, we try to find a new path with the aforementioned algorithm. And this path, of course, induces some cost, because maybe the path wants to travel to a station that is not yet open. So in order to do this path, we'd have to open the station, and this is all represented in this path cost, you could say. And if we do not have enough budget to actually add the path, we must try to repair the path to make it budget feasible by, say, removing individual trips. Or in general, you could also just say that if you find such a path, you stop the algorithm. If you, on the other hand, find a path that is within your budget limit still, you add it to the list of these paths. You make the appropriate changes to the infrastructure, so you build additional stations and charging slots so that the path can actually be done. You remove all the trip arcs that correspond to the trips that are already performed on the path, because obviously you can't do a trip twice. You also have to remove the waiting arcs from those stations that are already saturated. And you continue this process until you run out of budget, and that gives you an initial solution and a set of feasible paths throughout the network. Okay. And now, finally, a second thing we tried for improving the performance is symmetry breaking, because as you might have already noticed, since the cars are homogeneous, there's a lot of symmetry, because basically any path can be equally well performed by any of the cars. So one question is, of course, how can we prevent these symmetries? And one way of doing that is by adding constraints that impose an ordering on these constraints. So we always say that the value, and I'll get to what the value is, the value of a car with index k must always be larger, equal than, 8 of course, than the value of the next car. So that means that the car 0 has the highest value, and then car 1, 2, 3, and so on. And this value can, of course, mean different things. First, it might just be the number of trips that the car performs, or the collected profit of all the trips it performs. Of course, in case of the uniform profit, this is the same. Or the duration of all the trips it performs. So this guarantees us that we lose a lot of these symmetries by just making sure that if there is, in the optimal solution, one path with 4 trips and no other, then car 0 has to do it. But so far, it's not looking all that good. I don't have tables for this so far, but suffice it to say, in general, it triples or quadruples the necessary runtime, and we have never seen any real improvements, which is also consistent, I think, with what the colleagues here in Bologna have seen with their experiments. So this is apparently not a good avenue for improving the performance. All right, so this already brings me to the end of this talk. So far, it's certainly an interesting question to be solved, but there's still some work to be done to get it to work on more realistic instances, you could say. Of course, to make it more realistic, we also have to think about some possible extensions. For instance, integrating uncertainty. As I already mentioned, the set of trips is assumed to represent some kind of expected trips in the future, and of course we can never know that for sure. So one obvious way to extend the model is to integrate this kind of uncertainty, to just say that we're not guaranteed that a trip might actually happen. Another aspect which we want to integrate is the aspect of relocation, because right now a car can only travel from one station to another if there's a trip that allows him to do that. And of course this might lead to a situation where in the morning everyone drives from the place in the city where people live to their workplace. The cars stay there all day, and in the evening they drive home, and throughout the day no one can use the vehicles because they're parked somewhere outside of the area where people actually want to use them. And this is actually something we're working on together with the University of Bologna, and we're working on these integrated models right now. Of course, results are still out, so we'll see what that brings. And again, so far we've mostly been focusing on artificial instances, and we'd like to test our algorithms on real-world data, because maybe there is some structure to them that makes it easier for us to deal with them. And we do already have some data that is based on taxi trip data and the actual street network of Vienna and Manhattan. We also want to think about some computational enhancements which I already mentioned, such as the constraint separation for the fractional case, and we hope that we see some improvements there. And finally, of course, we also have to think about alternative formulations, and in this case, especially some column generation approach, which we are currently exploring, and potentially even extend this to a branch and price framework image. All right, this is it from me. If you have any more questions, please feel free to ask, and thank you all for your attention.
Jonas.
I have two questions. Like first, relocation. Can't you just add trips with negative cost? So to model that you have a driver which drives the car.
Of course, in principle, this is possible to just model this in that way. There are two problems with this. First, of course, you need to ensure that the driver is actually there at the point where you want to relocate. So you have to synchronize your car movements with the driver somehow. And secondly, there's a lot of potential relocations, especially if you consider, say, a time period of a week and 15-minute time slots. So this makes the already huge problem even more huge. So it's in principle what we've been trying to do.
Yeah, probably you want to do something more clever. I agree.
We kind of want to do something more clever because it probably won't work that way.
So the second question is, the crucial assumption in your model is that the operator can choose the trips.
Yes, this is true. We
So
assume that...
that's not really realistic, right?
Well,
Nowadays.
no, it's not realistic in the sense that, of course, you can never be sure that a user actually does what you want him to do. This is, again, the problem of the trips representing some kind of expected trips in the future. In principle, this is a huge problem. Assume, for instance, that we assume that a trip takes place, and in reality it just doesn't, but we need that trip to relocate a car from some position to another where it's used for 10 more trips. This, in the end, has to be somehow modeled with uncertainty, we believe. But we're not there yet.
Yeah, I'm just wondering, I mean, if you have only low battery left, but it's enough for a short trip, you can select a short trip.
Sure.
But in reality, a customer can want to go anywhere, and if you don't have enough battery to take you to the other side of town, what do you tell him? Like,
well, in principle, this I think can be realistically assumed that the customer knows the battery that's left on the vehicle when he wants to order it. This is the case for Car2Go, for instance. So you always...
But for Car2Go, I mean, you can recharge when it has like 25% battery left, which for Smart in the city, I mean, you need a really big city to need a quarter of a tank to use that in one trip.
That's true. I mean, for electric cars, of course, this they don't have as much range as normal vehicles. So there it might be a problem more often. But again, I think if you want to book a vehicle and you see it only has 15% capacity left, and maybe you can even estimate how far that gets you in that vehicle, and the customer sees, oh, it's just 10 kilometers, but I want to go 25 kilometers, then I'm just not going to book this car. Again, it's somewhat...
I don't see it in the current models for this car sharing stuff. Like, that works very, very differently. There, the promise is you don't have to care about anything. Take a car, drive where you want, don't think about it.
Yes, but it's incredibly hard to actually model this, because you have to assume that any car can be at any place at any time. So, yeah, if you want to model it with the approaches I've presented, your graphs, for instance, become unmanageably large. But of course, it's something to think about in the future, and we kind of hope to improve on this work so far, because, as I said, the results so far don't look all that promising. Mm-hmm. But we believe that this is just a first step, and that we can improve this later on. Any more questions?
Yes. Please.
Yes.
How does the computing time depends on the length of the period and also on the value of the budget?
Well, in this case, all the instances had about the same length, the same number of time periods. The budget, of course, is an important factor. If the budget is too large, then you can buy, say if there's 100 trips and you have enough budget to buy 100 cars and open all the stations, then of course it's trivially possible to perform all the trips. So of course, the hard part is, say, the middle of the budget range. If it's too high, then it's too easy because you can do everything. If it's too low, then you are so constrained in your choices that there is not much to be optimized. And for instance, the results I showed you, for these instances we computed the minimum budget required to cover all the trips. So we made a run without any budget limit and saw how many trips we could actually cover at most. And then we reversed that and said at least this many trips have to be covered and minimize the budget. And we took this budget as our maximum budget ever required. And for the instance you just saw, 0.5 of that maximum ever needed budget was used. So yeah, so we assume that about say half of the stations can be built for that budget. And of course it does introduce lots of problems, because if you do not constrain the budget at all, most of the runs finish in 20 seconds. But this is of course not very interesting because there's not much to be optimized. Does that answer your question?
Another question?
Yes.
Actually, you're solving instances which are quite small in terms of
yes, they
number
are
of
quite
trips.
small.
But which is the size of realistic instances? Because if you want to use a model to derive information about strategic planning, you cannot consider 100 trips, which is the number of trips of one day. So you should consider 1 year.
Exactly. I can just tell you about the instances with the realistic data we have. This is taxi trips for the whole city of Vienna for 1 year, and that's about 25,000 trips. So this is the kind of instance you'd want to be dealing with. But of course, this is so far out of the question. Yeah. But I think one interesting aspect would also be to consider, say, scenarios. You consider trip scenarios for weekdays, for weekends, for holidays, for winter and summer, and look at how well do these strategic decisions work for each of the cases. This is also something we thought about previously, but we haven't done so far.
So the model is for validation of...
No, the model
No.
in principle is for optimization.
Okay.
But of course it's rather easy to extend this to such a scenario approach where you just have different scenarios and each just consists of a set of trips. And you just try to find the optimal solution that, say, covers over all these scenarios with the most trips. Or, on the other hand, that tries to find the cheapest possible solution to cover 80% of the trips in each scenario, or something like that.
More questions? None from the web, so thanks again. Great. Jonas, stop.
Stop.